Hello, everybody, and welcome back. Hopefully, we're all having a good weekend. So we're getting close to the end. Um, we just have a couple more weeks left of videos and quizzes and whatnot, and then it would be summer. It seems like it's gone by so fast. Hopefully, we can all have a good summer and um, with restrictions starting to lift, and we can kind of be safe and enjoy the weather and enjoy our summer. So, with that in mind, let's push on through to the end. So today we're going to talk about something called Pascal's Triangle, and then from there we are going to talk about binomial expansion. So Pascal's Triangle, what is it? Well, Pascal's Triangle is a triangular arrangement of numbers constructed in such a way that every number in the interior of the triangle is the sum of the two numbers directly above it. It has many applications, including determining the coefficients of the expansion of a binomial expression, or finding the number of ways to choose m objects from a group of n indistinguishable objects. Now, that might sound familiar, right? Finding the number of ways to choose m objects from a group of n indistinguishable objects, right? That's what we were talking about last week, right? When we're trying to figure out the number of ways of choosing locker combinations or the number of ways of making a committee or things like that. The Pascal's triangle actually ends up giving us in those groups. It arranges the numbers in a way that it actually ends up giving us the answers to combinations. So let's just take a look at Pascal's triangle real quick. So this is Pascal's triangle here. This is the first 1, 2, 3, 4, 5, 6, 7, 8, 9 rows of the Pascal's triangle, where we start with the number 1 on the top, and then the next row is just two ones, and then the row underneath of that, what you'll notice is that 1 and 1 gives us 2. Right, so here's the Pascal's triangle. So this is, again, these notes that I'm showing you guys are notes that I would have in class. So this would be kind of the interactive part where I'd say, all right, identify 3 patterns. So if you want to just kind of stop the video and take a look and see, okay, well, what's going on here, and take a look at the Pascal's triangle and see if you can't figure out some patterns. And then once you're ready, start the video back up and we'll talk about it. So there's some interesting things that happen in Pascal's triangle. So the first one I pointed out is that when you take a look at any two numbers in your Pascal's triangle, and then you look at the number underneath of those two, it is the sum of the previous two numbers. So for example, this 2 is the sum of 1 plus 1, right? This 3 is 1 plus 2, this 4 is 1 plus 3, and this 6 is 3 plus 3, right? But there's also some other patterns going on here, right? If you look down the exterior side to the Pascal's triangle, it always starts with a 1, right? But then if you look down the next row in, you'll notice that we are just increasing by 1 each time. So 1, 2, 3, 4, 5, 6, 7, 8, and so on, right? And the same thing goes down the other side of the triangle. The triangle is symmetrical, right? So the left-hand side and the right-hand side, whether you're coming at it from left to right or right to left, you'll have the same numbers, right? So there's a lot of interesting things that happen within Pascal's triangle. But this is just kind of the surface of it. There's some other really cool things that are going to happen that we're going to take a look at. So again, something that we talk about in class would be, I give you a few questions, like, oh, what's this? What's that? So one row of Pascal's triangle is 1, 12, 66, 220, so on, so on, so on. Which row is it, right? So what row would this be? So if you're taking a look at Pascal's triangle, we would start off here saying that this is the 0th row. It's kind of a weird thing to think about. This isn't actually what we consider the first row. This would be the 0th row, and then the next row down would be the first, and then the next row down would be the second, and then the third, and so on and so on and so on. So using that pattern, which row would this be? Well, the nice thing is we always start with a 1, and then the next number over is the row number. So the second row, there's a 2. Third row, there's a 3. Fourth row, there's a 4. Fifth row, there's a 5, and so on and so on and so on. So for this row right here, obviously this would have to be the 12th row. And what would happen if we followed this pattern where the next row is the sum of the two previous numbers? What you'd find is that if you went down to row 12, you would get these numbers. Now, what would the next row look like? So then how would we find that? Well, we know the first number would have to be a 1, and then the next number would have to be a 13 because it's the 13th row. But then where do we go from there? Well, we just have to look at the previous two numbers. So the next number is 12 plus 66, and then the next number is going to be 66 plus 220, and then 220 plus 4 is 95, and so on and so on and so on. And then to find the previous row, though, what we'd have to do is a little bit of investigation because we couldn't just look at the list of numbers and say, okay, well, 66 minus 12 or Not like we could go forward, but what we could do is we would know that the first number would have to be 11, and the next number would have, sorry, the first number would have to be 1, and then the next number would have to be 11. And then from there, we could do a little bit of kind of guesswork to say, okay, well then how did we get the 66? It'd be 11 plus what? How did we get the 220? It'd be whatever number we got plus what, right? And then we'd have to kind of do a little bit of guesswork and go backwards there, right? So here's some really interesting, one of these kind of deeper level patterns that are going on in this Pascal's triangle that makes it quite interesting. So determine the sum of the numbers in each horizontal row. So if I looked at each row in my Pascal's triangle and I looked at the sum of the numbers, so the first row is 1, and the next row is 1 plus 1 is 2, and then 1 plus 2 plus 1 is 4, and then 1 plus 3 plus 3 plus 1 is 8, and then 1 plus 4 plus 6 plus 4 plus 1 is 16, 32. And you'll notice that there's even a pattern going on here, right? What pattern do you see? So what do we notice here? Well, each time we go down a row, the sum of the numbers gets doubled, or more specifically, each row is a power of 2. The sum of the numbers in the row is a power of 2. So the 0th row adds up to give us 2 to the 0. The first row adds up to give us 2 to the 1. The second row adds up to give us 2 to the 2, and then 2 to the 3, and 2 to the 4, 5, 6, 7, and so on. So if that's the case, what would the sum of the numbers in the 8th row be? Well, it'd be 2 to the 8. Okay? So each number in Pascal's triangle can be written as a combination. So this is the kind of the power of Pascal's triangle. And this is why in the first statement we said the number of ways to choose m objects from n group or from a group of n, right? Is because Pascal's triangle, not only is it the sum of the previous numbers, but any term in Pascal's triangle can actually be discovered or can be found by doing a combination, where the combination we're doing is NCR, right? Where n is the number of objects in the set and r is the number selected, right? So we did talk about that last week. Now, from Pascal's triangle, what we say is n ends up being the row number, and r ends up being the position in that row. So the first row of Pascal's triangle is 0, combination 0, 0, choose 0. And then the second row would be 1, choose 0, and 1, choose 1. And then 2, choose 0, 2, choose 1, 2, choose 2, right? And what you'll notice is if you did these combinations, we'd end up with 1, and then 1, 1, 1, 2, 1, and the next one, 1, 3, 3, 1. So the nice thing about this is now we don't need the previous row from Pascal's triangle to know what the next row is going to be. All we need to do is combinations, right? So again, they always start at 0. So the first row of Pascal triangle is actually the 0th row, and the first term from left to right is actually the 0th term, right? So just be aware that we're starting from 0 when we're doing these numbers. So the nice, again, like I said, the nice thing about this is now if I want to find any one term within Pascal's triangle, so let's say I wanted to do the 5th row, third term, right now instead of having to do, excuse me, instead of having to make my Pascal's triangle 5 rows deep, I can do 5C3, and that'll give me my answer. Okay, so here's an example. The third element in the 9th row of Pascal's triangle. So if we're starting at row 0, right, we're starting at term 0, right? So the third element in the 9th row. So not the third term, the third element. So if we think about this for a second, in the 9th row of Pascal's triangle, we're saying that that's 9C0, 9C1, 9C2, 9C3, and so on and so on and so on, right? So in this pattern, the third element is 9C2. So to answer question A here, we would have to do a combination of 9C2, and we could plug that into our calculator, or we could do our formula for combinations. 9 factorial divided by 9 minus 2 factorial divided by 2 factorial. So this is 7, so we get 9 times 8 over 2, which is 36. Okay, so the third element in the ninth row of Pascal's triangle is going to be 36. Right? And if we're not convinced, if we take a look at our Pascal's triangle from this slide here, right? If we took the ninth row, which is this is the eighth row, so the next one's going to be 1, 9, and then 8 plus 28 is 36. Okay, so same thing here, the seventh element in the 15th row. So the 15th row is going to be 15, choose 0, and then 15, choose 1, and 15, choose 2, and so on and so on and so on, where the number of the element is 1 minus 1 is my R, right? So my R value for my combination is going to be the element number minus 1. So if I'm looking for the seventh element in the 15th row, I'm looking for 15, choose 6, not 7, right? Because it's minus 1. So again, 15, choose 6. We could do our formula. Now it's going to be a little bit easier just to use your calculator. So if I do 15 C6, I get 5,005. Okay. And then part C here asks for the first 5 elements in the 20th row. I'll leave that for you guys to try. The first 2 should be easy enough. It's going to be 1, because it's always 1. And the next one's going to be 20, because we're talking about the 20th row. So that second term's always going to be equal to the row number, right? So then it's just a matter of finding elements 3, 4, and 5 by using our pattern, right? 20, C0, 20, C1, 20, C2, 20, C3, and 20, C4. Right? So then it's just a matter of plugging those into your calculator and solving. Okay, so why do we care? I guess that's one of the questions that we get a lot in math is like, okay, cool, there's a pattern, but why is this helpful? So here's why this is helpful. It's something called the binomial expansion. A binomial expression is the sum or difference of two terms, right? So we should be comfortable with the definition of a binomial expression. A binomial is anything that contains two terms, right? So the prefix bi meaning two. So for example, x plus 1, 3x plus 2y, a minus b, these are all binomial expressions. They could have variables, they could have constants, they could have a combination of the two, right? Generally speaking, you're not going to have a binomial that's just constants because that could be simplified, but you could if you wanted to look at something a little differently, like if you wanted to take the number 5 and say, well, 5 is equal to 2 plus 3, so then how can I use that to help me solve, right? So there's all kinds of ways of denoting a binomial expression, but in general, it's just two terms, right? So we should already be familiar with one process in which we want to expand binomials, right? X plus 1 squared. We've done that. We've been doing that for a number of years now. You might have seen the acronym FOIL to help us remember how to do this, but basically what we do is we take the x plus 1, and instead of writing it as x plus 1 squared, we write it as x plus 1 times x plus 1, right? And then the same thing for the x plus 1 cubed, right? So for x plus 1 squared, we say that that's going to be x plus 1 times x plus 1. And then we just go through and we say, well, then x times x and x times 1 and 1 times x and 1 times 1. So we get 4 terms. And then we combine like terms and we get something that looks like this, x squared plus 2x plus 1. And then for x plus 1 cubed, we would do exactly the same thing where we say it's x plus 1 times x plus 1 squared. Well, we just solved for x plus 1 squared. We know it's this thing here, so then we can replace it and then multiply that by x plus 1. So then what I'd have to do is I'd have to say x times x squared and x times 2x and x times 1 and 1 times x squared and 1 times 2x and 1 times 1, and I get this big long thing here. And then I would take that and combine like terms and end up with this thing here, right? So that's all well and good. I mean, it's something that we've been doing for a while now, and we should be somewhat comfortable with it. And it's not the process that takes the longest, right? It's a bit of a pain having to do that. I mean, when we're squaring it, we foil, we got that. It shouldn't be too bad. We go to cube it. All right, it takes us a couple extra steps, but again, not too bad. But If you want to determine the expansion of something like this, where we have not power 2 or 3 or even 4, what if the power was 6 or 7 or something that's even higher? What we would find is that we would get into a situation where it would just be tedious. It'd be cumbersome to do all that work and repeatedly multiplying x plus 1 by itself over and over and over. But maybe you recognized it, maybe you didn't. There is a pattern going on with these expansions that might just link back to Pascal's triangle. So just take a look at these for a second and see if you can't recognize the pattern that's going on. We'll discuss it here in a second, but it might be worthwhile just to take a look and be like, well, I wonder what's happening. Okay, so if we take a look at a binomial expansion for a second. So if we had x plus 1, and we're just going to work with x plus 1, right? So exploring x plus 1 to the power n, so any power. Notice here that when it's x plus 1 to the 2, it's 1x squared plus 2x plus 1, right? I specifically have this 1 here, so hopefully we are recognizing something. And then when it's the power 3, it's 1, 3, 3, 1 are the coefficients in front of my x. And if I look at power 4, something else, this pattern kind of continues on and on and on. And what you'll notice is that the coefficients that are in front of the x actually end up lining up with the numbers in Pascal's triangle, right? So Pascal's triangle can be used to determine the coefficients of each term in the expansion of x plus 1 to the power n. So if we take a look at this table here, right, I should say left, right? So if we take a look at this table here, what we notice is that all the coefficients when we're doing a binomial expansion are the numbers in Pascal's triangle. So there's a certain power to that, right? Now, if I gave you x plus 1 to the power of 6, right, you wouldn't necessarily need to do all of the expanding to find the coefficients, but we don't necessarily know what the x's are yet, right? Because it's like, well, where does the x to the 6 go? Where does the x to the 5 go? Where does the x to the 4 go? Like, where are these things? Well, again, there are other patterns that are developing when we do these binomial expansions. So let's take a look. For each expansion, what happens to the exponent on x as you move through each term from left to right? So if I take a look at the first one here, first it's an x squared, then it's an x to the 1, then there's no more x's. Then if I look at to the power 3, it's x to the 3, x to the 2, x to the 1, no more x's. If I look to the power 4, x to the 4, x to the 3, 2, 1. So if I were talking about, say, x plus 1 to the power 5, well, my first power of x is going to be x to the 5. And then my next power of x is going to be x to the 4. And then x to the 3, and x to the 2, and x to the 1. And then finally, the last one is actually x to the 0, right? But when you have something to the power of 0, that's just equal to 1, so we don't generally write it in. For each expression, how are the coefficients related to Pascal's triangle? Well, we talked about that. The coefficients are the numbers in Pascal's triangle. So for the second, so if we have a power of 2, we're talking about the second row of Pascal's triangle. If we had the power of 3, we'd be talking about the third row of Pascal's triangle, and so on and so on. Right? If we had the power of 1, that's just the first row of Pascal's triangle, or n x plus 1 to the power of 1, well, it's just x plus 1, right? So if we compare the number of terms in each expression to the exponent, what do we notice there? So, for example, if I have x plus 1 to the power 2, well, how many terms are in my expanded expression? There's 1, 2, 3 of them. X plus 1 to the power 3 has 4 terms. X plus 1 to the power 4 has 5 terms. X plus 1 to the power 6 has x plus 1 to the power 5 has 1, 2, 3, 4, 5, 6 terms. So what we end up finding is that the number of terms in an expanded expression is going to be 1 more than the power. So with that in mind, let's see if we can't do what the previous question suggested would be tiresome or tedious if we were to just expand it like we used to. And let's use Pascal's triangle to help us do that. So in order to do this, we would need to know what the sixth row of Pascal's triangle is. So 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, and finally 1, 6, 15, 20, 15, 6, 1. Right, so now what we know is that x plus 1 to the power 6 is going to have 7 terms. It's going to have 1, 2, 3, 4, 5, 6, 7. And the operation that's in between each term is a plus. So we're going to have plus, 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 plus. We know the coefficients are going to match the sixth row of Pascal's triangle. So it's going to be 1, 6, 15, 20, 15, 6, 1. And we know the power of x is going to start at 6 and go down by 1. So it's 1x to the 6, 6x to the 5, 15x to the 4, 20x cubed, 15x squared, 6x plus 1. And that is the expansion of x plus 1 to the power 6. Okay, now that's a very narrow range, right? It's x plus 1 specifically. So the previous slide was x plus 1 being put to the power n. But what happens if we look at some other binomial where it's not just x plus 1? What if it's anything plus anything, right? So a lot of the patterns that we noticed in the previous slide will still hold true, but we have to kind of add a little bit more to it, right? So for example, so if I had x plus y to the power 0, well, that's equal to 1. X plus y to the 1 is x plus y, so those two should be relatively obvious. X plus y squared, again, what we could do is if we're not sure, we could always just expand, right? FOIL, x times x, x times y times x, y times y, so we get x squared plus 2xy plus y squared. And again, what we're noticing here is that this is creating our Pascal's triangle, right? So this is 1x and 1y, so we have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. So again, what's ends up happening here is we are dealing with Pascal's triangle again. So what happens to the exponents on the x as you move through each term from left to right? So if we look at the exponents on the powers, the powers of x, as we move to left or right, what happens? So for example, if I looked at this one here, the final one, x plus y to the power 5. We have x to the 5, x to the 4, x to the 3, x to the 2, x to the 1, and then finally x to the 0. So as we move from left to right, the powers decrease by 1, right? So every time we go to the next term, the power of x is going to decrease by 1. What happens to the powers for y? Well, as we move from left to right, we notice that this is y to the 0, y to the 1, y to the 2, y to the 3, y to the 4, y to the 5. The powers increase. As we move from left to right, the powers will increase by 1. So they kind of do the opposite, whereas the x's are getting smaller and smaller and smaller, the y's are getting larger and larger and larger. Okay, so for part C here, compare the number of terms in each expression to the exponent in which the binomial is raised, right? So again, just like with the previous slide, the number of terms in each expression is going to be one more than the power on the binomial, right? So like x plus y to the 5 had 1, 2, 3, 4, 5, 6 terms, and to the 4 had 5 terms, and the 3 had 4 terms, and so on and so on. So finally, for each expansion, how are the coefficients related to Pascal's triangle? Well, again, just like the previous slide, the coefficients are the terms in Pascal's triangle, where the 0th row would be 1, and then 1, 1, and 1, 2, 1, and 1, 3, 3, 1, and 1, 4, 6, 4, 1, and so on and so on and so on. So the patterns that existed in the previous slide still exist. The only difference now is we're adding in more than one, more than just a 1. We're having a y or some other value in the powers. What we notice is that as the powers on x's decrease by 1, the powers on the y term actually increase. They do the opposite. So, for example, use Pascal's triangle and the patterns observed previously to expand to this thing. So let's try to expand a plus b to the power 7. So if we start putting everything together, a plus b to the power 7 is going to have 1, 2, 3, 4, 5, 6, 7, 8 terms, right? There's going to be one more than the power number of terms, and each term is going to have a to the 7, b to the 0, a to the 6, a to the 5, right? So your powers of a are going to go down by 1, a to the 3, a to the 2, a to the 1, and a to the 0. And your powers of b are going to go up. So this is b to the 0, b to the 1, b to the 2, b to the 3, b to the 4, b to the 5, b to the 6, and finally b to the power 7. Each term is going to be added. Now, there's an interesting thing that's happening here that can kind of help us if we're a bit lost about, okay, what should the power be for this one again? Recognize here that a to the 7, b to the 0, 7 plus 0 gives us back to our original 7. A to the 6, b to the 1, 6 plus 1 is 7. 5 plus 2 is 7, 4 plus 3 is 7, 3 plus 4 is 7, 2 plus 5, 6 plus 1, and 7 plus 0, right? So then what's happening here is every combination of power should always add up to get me back to the 7. Okay, so we have our A's, we have our B's. The last thing we need to do is find our coefficients, right? So again, we use Pascal's triangle. So 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, and 1, 7, 11, 25. Sorry, that should be 15, not 5. So 1, 7, 21, 35, 35, 21, 7, 1. So now we have our coefficients. They're contained within the Pascal's triangle. So 1, 7, 21, 35, 35, 21, 7, and finally 1. And that is the expansion of a plus b to the power 7. And hopefully what you're recognizing is that this tool is much more powerful than taking this and turning it into a plus b multiplied by itself 7 times and going through that vertically down a page, right? It would just be so tedious and so cumbersome to do that. Now we have this nice tool that allows us to do it much more efficiently and much more quickly. So this kind of leads us finally into what's called the binomial theorem. So if we wanted to expand a binomial expression with a large power, so not like 3 or 4 or 5 or even 7, because even 7 didn't take us too long to deal with Pascal's triangle, but something like x plus y to the power 32. Just this massive, massive, massive power that, again, if we're doing this with the intentions of saving ourselves time, trying to create a Pascal's triangle that has, 33 rows, because we're starting with row 0, that in itself would take us a long time. So the use of Pascal's triangle would not be recommended because of the need to generate large numbers of rows of the triangle. So we have an alternative method called the binomial theorem. And what the binomial theorem says is it kind of just gives us a formula. It says any expansion of a binomial expression to a power n can be written like this. And again, we've talked about how the numbers in Pascal's triangle relate back to combinations. So what we can do is we can use that to, instead of actually creating Pascal's triangle, we can use the combinations in the place of writing the Pascal's triangle out, where the coefficient of your first term is going to be nc0, where n is the power of your binomial expression. And then nc0, x to the n, y to the 0. And then nc1, x to the, and then we're going down by 1 and up by 1, right? And then nc2, we're going down by 2, up by 2, and then down by 3, up by 3, and so on and so on and so on. And then the pattern is going to go from right to left in the opposite way, where the y will be put to the n and the x to the 0 from the right-hand side, and then the numbers on the y will go down by 1 as we go from right to left, and the numbers x's will go up by 1. And your coefficients will also match going from right to left that they will from left to right, because that's, again, the nature of combinations where we have this pattern where NCN is the same thing as NC0, right? This is n items choosing 0. Well, there's only one way of doing that, right? It's picking none of them. This is n items choosing n of them. Again, there's only one way of doing that. It's by picking all of them, right? So in general, any one term in a binomial expansion can be written like this, where we have a coefficient that is nck, x to the n minus k, y to the k, where k plus 1 is the term number. So k plus 1 is the term number. So the term number is not equal to k, right? The term number is 1 plus k. So for example, the first term, k is 0, right? The second term, k is 1. The third term, k would be 2. So if I wanted to expand this thing now, so now what we have is we have not just x's and y's, but we have variables and numbers. So we're going to use these same rules where the number of terms is going to be 1 more than the power. So we're going to have 1, 2, 3, 4, 5 terms here, right? But then what's going to happen is that we're going to take a look at the 2a as the first term of my binomial, and 5 is the second term. So when we're putting something to a power, it's going to be all of 2a to the power of 4, and then all of 2a to the power 3, and then all of 2a to the power 2, and then all of 2a to the power 1, and then 2a to the power 0 is 1. And then same thing with the 5, right? So this is 5 to the 0. This is going to be 5 to the 1, 5 to the 2, 5 to the 3, and then finally 5 to the 4. And again, we can check to make sure that these are right because our exponent should add to give us 4 each time. So 4 plus 0, 3 plus 1, 2 plus 2, 1 plus 3, 0 plus 4. And then we need to find the coefficients. So again, what we say is the first term is going to be 4c0, 4c1, 4c2, 4c3, and finally 4c4. So now let's expand and simplify. So 4c0 is 1, 2 to the 4 is 16, and a to the 4. So this thing is going to be 1 times 16, so 16a to the 4. Plus 4c1 is 4, 2 to the 3 is 8, and 5. So it's 4 times 8 times 5. So 4 times 5 is 20, times 8 is 160, a cubed. Plus, so 4c2 is 6, I believe. But let's check that, plug it into our calculator. So 4c2, we get 6. So this is 6. 2 squared is 4, right? 5 squared is 25. So 4 times 25 is 100, times 6 is 600, a squared. Plus 4c3 is 4. 2 to the 1 is 2. And 5 to the 3 is 125. So 125 times 2 is 250. And 250 times 4 is 1,000. A. And then finally 4c4 is 1. 5 to the 4 is 625. So then there is my expansion for 2a plus 5 to the power 4. So that's not the only thing that we could do with a question like this. Instead of saying to expand, I might just ask you find the nth term, whatever term number I'm looking for. So for example, find the 8th term. So in this expression. So again, what I can do is say, okay, well my term number is going to be equal to k plus 1. So I'm looking for when k is 7. So then now I know I'm looking for the term that contains 13c7 x to the 13 minus 7 y to the 7, right? Where I'm using that binomial expansion or binomial theorem, this thing right here. Okay, so then it's just a matter of doing 13c7 in our calculator, and we get 1,716 x to the 6, y to the 7. So that would be the 8th term in this binomial expansion. Okay, so here's a couple of practice questions that I would suggest you guys try. So pause the video. I'll go through the answers here in a second. So once you're ready, start the video and check your work against mine. Okay, so let's do these relatively quickly this time. So again, what I'm going to do is I'm going to take each of these terms. We have power of 5, so I'm going to use that binomial theorem. So it's going to be 5c0, 3a to the 5, plus 5c1, 3a to the 4, negative 4b. Notice here that we have a minus symbol, so that's going to affect our question. Plus 5c2, 3a to the 3, negative 4b squared, plus 5c3, 3a 2, negative 4b cubed, plus 5c4, 3a, negative 4b to the 4, and then finally plus 5c5, negative 4b to the 5. Okay, so now it's just a matter of pulling our calculator and doing the work here. So 5c0 is 1, so we get 3 to the power 5, and we get 243 a to the 5, plus 5c1 is 5 times 3 to the 4 times negative 4, and we get, so this time it's going to be minus because it's negative, so minus 1620 a to the 4b. And then 5c2 times 3 to the power 3 times negative 4 squared, so 16, is 4,320 a cubed b squared. And then the next one's going to be minus because our negative has an odd power, so 5c3 times 3 squared times 4. Negative 4 to the power 3 is negative 5,760 a squared b cubed. Starting to run out of space here. So 5c4 is 5, so it's 5 times 3 times 4 to the 4. So plus again because it is a even power on the negative term there. So 3,840 a b to the 4. And then finally my last term is going to be 5c5, which is 1, and then 4, negative 4 to the 5 is minus 1024 b to the 5. Okay. So part B says, what is the third term in this expansion? Right. So again, if we're talking about the third term, that means k plus 1 is going to be equal to 3. So then k is 2. So now we're saying 6c2 5a squared. So the squared is a part of our expansion, so it needs to be there. 5a squared to the 6 minus 2, and 2 to the 2. Right, so now it's just a matter of using our calculator. So 6c2 times, so this is 5 to the 4, and then times 2 to the 2 is 37,500, and this is a to the 2 to the 4, so a to the 8. Now, part C is a little different. We haven't seen one quite like this before. But again, what we need to do is, in the expansion of a squared minus 2 over a to the power 7, which term in simplified form contains a to the 5? So again, what we know is that NCK A squared to the power 7 minus K times 2 over A, and that's going to be a negative, to the power K, right? That's our binomial theorem. So what we can do now is say, okay, well, when will this thing have a variable that is A to the 5? And there's a couple of things that we can leave out, right? There's a couple of things that we can leave out here. Because we are just looking for the variable, we really don't care about the NCK, right? It's not going to tell us anything and about the variable. It's going to tell us something about the coefficient. So we don't really need to concern ourselves with that right now. We also don't really need to concern ourselves with the 2, and we also don't really need to concern ourselves with the negative, because all we will need to find for this question is when will we have a simplified variable of a to the 5, right? So now what I know is that when I multiply these things, I'm going to get a squared to the power 7 minus k over a to the k. So now what I need to do is figure out, well, when will this thing equal 5? So if we use our exponent laws, right, this is going to be a to the 14, right? So if I expand this, it's 2 times 7 and 2 times negative k over a to the k. Okay, so now, again, these both have the same base. So what can I do with their exponents if they have the same base? I can add or subtract if I'm multiplying and dividing. So this thing simplifies to give me a to the 14 minus 2k minus k. And then that, we want to know what value of k is going to make this thing a to the 5. So now it's just a matter of solving. 14 minus 3k is going to be equal to a to the 5. Sorry, it's going to be equal to 5. So I subtracted 14 from both sides, and I get negative 3k is going to be equal to negative 9, or k is 3. Right? So we now know that when k is 3, that's when we're going to be left with an a to the 5. So then it's just a matter of saying, okay, well, if k is 3, and we know our term number is equal to k plus 1. So 3 plus 1 is term 4. That will contain the a to the 5 variable. All right, so that is it for this week's content, binomial theorem. Next week, what we're going to be taking a look at is we are going to dive into some functions, rational functions, inverse functions, things like that. Okay, so I'll post the week's kind of work along with this, and we'll have our session on Wednesday, just like always. All right, and I will see you guys then. Have a great